Okay, so let's take a look at this sample problem. So actually, it is an extension from the 2302. So hopefully you can remember this cube. It asks what is the net charge enclosed by the Gaussian cube SP of SP 2302. Okay, so according to that sample problem, we have already calculated something. The phi left, the total flux for the left surface, the total flux for the right surface, and then the total flux for the top surface. So actually, there are six surfaces for a cube. Okay, so we need to calculate the remaining three. So obvious that phi front and right and phi back. This one should be back. Okay, is 0. Okay, so front means this one. Okay, this is front, and then that one. That one is back. Okay, this is front. This is back. Clearly to be 0 because, for example, for the front, dA is actually like a dA times this is positive z-axis k or k hat. Okay, so if we have a k hat dotted with the E field would be like this. Okay, 3x I hat. Okay, only have I hat and j hat. So no matter which one dotted with k hat would be 0. Okay, so maybe let's cut this down. Okay. Okay. Ooh. Okay. Okay, so we have this. Okay, actually we have that here. Okay. Yeah, so no matter which one dotted with the k hat will be 0. So it is clear that phi front, phi back must be 0. Okay, so the remaining one is left, right, top. Okay, so the remaining one is bottom. Bottom. Okay, the bottom one. Okay, bottom one is here. Actually, dA will be like negative dA negative y direction, negative j hat. Okay, like this. Okay, so we have actually integration of 3x I hat plus 4j hat dotted with negative dA j hat, something like this. Okay, and then for the bottom. Okay. Yeah. So I hat dot j hat will be 0, and then the remaining one. Okay, integration of 4dA, 4dA for the bottom surface. Okay, so we can quickly see that this is negative 4 times 4, which is negative 16 nm squared over c. Okay, so this is for phi bottom. So the total flux, or the net flux. Okay, the net flux will be adding all this number together, which is negative 12 plus 36 plus 16, and then plus 0 plus 0, and then minus 16. Okay, will be. Okay, so these two cancel out, and then this one turns out to be 24 nm squared over c. Okay, so this is the net flux. Actually, this is not the answer. It asks you the Q in charge, or the charge inside this cube. So Q enclosed will be epsilon naught phi. Okay, which is 8.85 times 10 to negative 12. And then times 24. So which is 2.1 times 10 to negative 10 coulomb. Okay, or if you would like to write it in the scientific prefix, which is 210 picocoulomb. Pico is 10 to negative 12. Okay, so you can either answer this one or this or that one. Okay, so actually this sample problem tells you that the Q enclosed is 210, but you have no idea how the charge are distributed inside the cube. You only know, okay, so the total amount of charge is inside, okay. So probably there should be some symmetry, okay, so to generate this if you like that, but yeah. So if we would really know how the charge distribute, we probably need to solve the Maxwell equation. Yeah, probably it's not easy to do it with hand calculation. Okay, so so next we talk about this one, which is about the charge, a charge isolated conductor. Okay, a charge isolated conductor. So here it says if an excess charge is placed on an isolated conductor. Okay, conductor. Conductor is a keyword. And then that amount of charge will move entirely to the surface, of the conductor. Okay, so this is a very important property, okay, for the conductor. Okay, so just imagine, okay, so this is the cross section. This part is the cross section of the conductor. It actually extends to far away, okay. So this is the only surface you can see at this point of view. Okay, it says that all the charge will go to the surface. Of course, it has a thickness, but the thickness wouldn't be so thick. But anyways, it mentioned that all the charge will go to the surface. It means that if there are some charge inside, and you can actually, let's say, draw a Gaussian surface inside the conductor, then okay, there should be some flux. Okay, there should be some flux. So which means that there should be some E field inside. As long as there are some E field inside, and then this will accelerate the charge. Okay, so that it will move. Okay, it will move so that it can be settled inside the conductor. Okay, so which means that inside a conductor, okay, all the charge will go to the surface. So inside the conductor, okay, the E must be 0. Okay, E must be 0 inside. Okay, so it can only generate some E field outside. Okay, so none of the excess charge will be found within the body of the conductor. Okay, the side view of a tiny portion of a large isolate. Okay, so another keyword is large. Okay, so which means infinitely large. Okay, isolated conductor with excess positive charge on this surface. So a closed cylinder, cylindrical Gaussian surface. Okay, so 一个圆柱形的一个Gaussian surface. Okay, so you can see, okay, half of the cylindrical is outside the conductor, half of the cylinder is inside the conductor. The conductor, yeah. So embedded perpendicular in the conductor. So sometimes before we have mentioned that the axis is like connecting all the center of a different circle. Okay, so this is the axis. So perpendicularly means the axis is perpendicular to the surface. Okay, we assume the surface is a plane. Okay, so electric field lines pierce the external end cap of the cylinder, but the internal end cap, but not the internal end cap. So the external end cap has the area A. Okay, so what it means is that we assume these parts. Okay, these parts have a surface area. Okay, has an area of A. Okay. And as much as this is like a plane and then infinitely large, so actually it should be symmetry. Okay, it should be symmetry. The E field should be also perpendicular to the surface. Okay, because no matter which point, okay, you put this cylinder on the inductor or on the conductor. Okay, you actually see the same thing. Okay, you actually see the same structure. Yes. You need to imagine. Okay, this conductor is very large. So no matter where you put, okay, just like you are on the Earth. Okay, you are so small compared to the Earth. So even though the Earth is a sphere. Okay, so you feel like, okay, so as long as you can see a very small area, so it's like a plane. It is like that case. So no matter you see at the top, at the down, left, right. Okay, so it is infinitely far away from you. Okay, so you can also imagine the charge is uniformly distributed on the surface. So what you see, okay, no matter how you shift the cylinder, okay, you see actually the same thing. Okay, so it should be some symmetry. Okay, and then the E field should be perpendicular. Okay, should be perpendicular. And as much as this is positive charge, so the E field should be points away. Okay, from the conductor. Okay, so here it try to apply the Gauss law for this cylinder. Okay, so actually just as what I mentioned, this one. Okay, maybe I use this color. Okay, so this one is inside the conductor. So just as what I mentioned, the E field inside conductor must be 0. So the flux, okay, so the E dot dA for this part is 0. Is 0. Yeah, because all the E field over the whole area is 0. Okay, and then for the side part, it would be perpendicular to the E field. So E dot dA must also be 0, even though the E itself is not 0 at this part. Okay, inside the conductor part. Okay, so even though the side plane. Okay, so half of it is inside, okay, half of it is outside. Okay, for the inside part, it is still E equals 0. But for the outside part, even though E is not 0, but it is perpendicular to dA. Okay, dA could be like, dA is like this, dA is like this. Okay, so it's all the way perpendicular to E field. So for the side plane, even though outside the conductor, the total flux, okay, will be 0. So the only remaining part is that part. Okay, is that circle. So we assume that E field is perpendicular, and then so it will be parallel to the dA. Okay, and actually they are pointing to the same direction. So actually it turns out to be like, so it could be like E dot dA. Epsilon naught E dot dA. So it turns out to be that part. Okay, that area. Okay, so we only have one part, and E dot dA will be like they are pointing to the same direction. So actually it's equal to E times dA, and E would be a constant. So we can move this E out. So it turns out to be E times epsilon naught E integration of dA, which is the surface area, so which is denoted by A. So we have epsilon naught EA equals Q enclosed. Here we also introduce the surface charge density. Okay, this is the surface charge density, if you still remember, in chapter 22. Surface charge density in chapter 22, okay, if you still remember. Yeah, so this is the surface charge density. As much as the charges distribute uniformly, so this sigma is also a constant over the whole surface, and multiplied by the area. Okay, so the surface charge density multiplied by the area will be the total charge amount on this surface. Okay, so we can see that from the leftmost part and the rightmost part. Okay, we have A and A to be cancelled. So we can move epsilon naught to the right side. We have this E equals sigma over epsilon naught, so which is quite similar. Okay, do you still remember this one when we try to calculate the E field generated by the disk? Okay, so of course this disk is not infinitely large. Okay, so in that case, if R is not infinitely large, we have the expression of E field along the z-axis like that. Okay, so we have this part and then 1 minus this stuff. Okay, related to the distance and then the radius. Okay, related to the geometric shape. Okay, if we assume R to be infinity, okay, so this part turns out to be 0 if R tends to be infinitive. Okay, so if you still remember in chapter 22. Okay, so turns out to be like this. Okay, but this one and this one has a factor of 2. Okay, why? Okay, the reason is that this is only a plane. Okay, this is only a disk, so it will generate the E field pointing upwards on the top side, and then also generate the E field downward for the bottom side. Okay, but here we assume that this conductor is infinitely large. Okay, so it only generates all the E field on the right side. So this is double. Okay, this is double. So this is sigma over epsilon naught. This is sigma over epsilon naught, also divided by 2. Okay, so this is only half, because half of the E field goes to the top side, half of the E field goes to the down side. So okay, total E field. Of course, you cannot directly add them together because yeah, this part is on the top, but that part is on the bottom. But totally, okay, they generate the same amount of E field. Yeah. Okay, so here we have a sample problem. Okay, so so here it says okay, the figures show the figure A shows a cross section. Okay, so the left one is figure A. So a cross section of the spherical metal. Okay, metal shell. Okay, so this is metal shell of inner radius R. Okay, so the inner radius R, a point charge of -5 μ coulomb. Okay, so this is the point charge. -5 μ coulomb is located at the distance of R/2 from the center of the shell. Okay, so not at the center. So if the shell is electrically neutral, what are the induced charge on its inner and outer surface? Okay, it actually tells you that the shell itself is electrically neutral, okay, so, which means the total charge on the shell should be 0. Okay, but it can be some induced charge. Okay, because this is a conductor. Okay, so so here are those charges uniformly distributed? What is the field pattern inside and outside the shell? Okay, so when we talk about the harmony induced charge, it is easier to understand. Okay, so the idea here is there would be plus 5 mu c on the inner surface, and thus negative 5 mu c on the outer surface because they must add up to be 0. Okay, so why is the inner surface has a charge of plus 5 mu c? Okay, we can actually assume a Gaussian surface inside the shell. Okay, inside the shell. Okay, so this is the Gaussian surface. This is the Gaussian surface we assume. Okay, and as much as what I've mentioned inside the conductor. Okay, so this is a metal shell. Metal is a type of conductor. So inside the conductor, the E field inside the conductor must be 0. So which means that over this Gaussian surface, okay, all the E field are 0. So which means that integration of E dot dA must be 0. So multiplied by epsilon naught is also 0. So according to Gauss law, the Q enclosed for this Gaussian surface is also 0. Okay, so Q enclosed is 0. So which means that we have already, okay, this is negative 5 mu c. Okay, negative 5 mu c. Okay, so which means that the inner charge, okay, inner induced charge, let's say we call it Q inner, should be positive. Okay, so that's the Q enclosed turns out to be 0. Yeah, because we have a negative 5 mu c and then plus Q inner. Okay, equals 0. Okay, so Q inner must be positive 5 mu c. Okay, and then thus, okay, Q inner and Q outer should add up to be 0. Q inner plus Q outer must add up to be 0 because this sphere is electrically neutral. Okay, so as much as this is positive 5 mu, and then this one should be negative 5 mu. So this is Q outer here. Okay, it's negative 5 mu c. Okay, so finally, what is the field pattern inside outside the shell? Okay, and then what are those charges uniformly distributed? So this is not easy to understand. Okay, so it only tells you that for the outer surface, the charges are uniform. The charges are uniform for the outside part, but for the inside part, that is not uniform. Okay, so as much as these negative charge are close to the left side, okay, there will be more positive charge concentrated on the left side. Of course, there will still be some positive charge for the other part. Okay, but the left part tends to be denser. Okay, so so you see that, okay, as much as this is a negative charge, the E field line will ends up at this negative charge, and then this part will have a stronger E field. Okay, those parts will have a weaker E field. Okay. However, for the outside part, okay, all the negative charge are distributed uniformly, so that if we just observe the E field outside this sphere, okay, it turns out to be like all the charge are like concentrated on the center. Okay, so the E field can be calculated as, okay, from the center. Okay, this is out. Okay, so this E field will be like E equals K times negative 5 mu c over R squared, something like that. Okay, something like that. Okay, even for this part, it will be the same thing. It will be the same thing. Okay, so this one we call it the shielding. Okay, the shielding. Okay, so as much as we have some conductor, okay, isolating some charge. Okay, so how the charge distribute inside the sphere isn't really important. Okay, from the outside, it's just like all the charge are concentrated at the center. Okay, so that it will make the outer surface have a uniform charge distribution. Okay, so this is a interesting phenomenon. Okay, so for some of our appliance or some of our let's say this or some equipment in the laboratory. Okay, so there should be some case to isolate the EM wave. Okay, using this shielding effect. Okay, this shielding effect. 中文我们叫做屏蔽效应，但 okay, of course it will not be asked in the exam. Okay, but as long as we try to design some chip, okay, we try to use some kind of shielding effect to isolate the interference between some high frequency signals. Yeah. Okay, so next we try to talk about applying Gauss law for different geometric shape. So the first one is the cylindrical symmetry. Okay, cylindrical symmetry. So here we have another three-dimensional coordinate. Okay, so the first you should be familiar with is the Cartesian coordinate, okay, Cartesian coordinate. So it will be like x, y, and z. Okay, x, y, and z. Okay, the other one will be like the spherical coordinate. Okay, the other one will be like spherical coordinate. Okay, 球坐标的话 actually is like x theta phi. Okay. And then this one is cylindrical. Okay, cylindrical coordinate. Okay, which will be x theta. Oh, sorry, it should be r. Okay, r theta. Okay, should be r theta and z. Okay, so it will be like this part is the polar coordinate. Okay, this part is the polar coordinate. In a two-dimension, r theta, okay, and then combined with an independent z-axis. Okay, so it is a little bit more complicated than the Cartesian coordinate, but easier than the spherical coordinate. Spherical coordinate will be like you have one radius. Okay, you have one radius, and then with theta and phi to be two angle. Okay, so we will slightly talk about it a bit later. Okay, so actually go back to here. So for the cylindrical coordinate will be like, okay, so this one will be the z-axis. Okay, this one will be the z-axis. So perpendicular to it, every surface will be like the similar to the xy plane. Okay, but actually we turns out to be use r and theta. Okay, so maybe starting from one x-axis, okay, there will be an angle of theta, something like that. But of course, this r theta here in this cylindrical, in this case is not really important. Okay, so actually we can just erase that part. Okay, so here it says a section of an infinitely long cylindrical plastic rod. Okay, so the keyword is infinitely long. Okay, cylindrical plastic rod with a uniform charge density of lambda. Okay, so we assume this rod is thin. Okay, it's thin. Okay, it's just a line. So this lambda is the linear charge density. So the rod, the charge distribution and the field have cylindrical symmetry. Okay, because this is infinitely long. So if we assume any Gaussian surface to be a cylinder, okay, so even though you move up, move down, okay, as long as this axis, okay, this axis is aligned with the rod, okay, so no matter how you move up or move down the cylinder, okay, it will see actually the same thing because the rod is infinitely long. Okay, so you move up, okay, you can still see infinitely long on the top, infinitely long at the bottom. Okay, you move down, okay, you still see the same thing. So it must be symmetry. So which means that it will not generate some component that is like in the c direction. Okay, so it must be the E field must be perpendicular to the c axis. Okay. So according to this symmetry. So and then also as much as this side, okay, this side is symmetry. Okay, so we also assume that okay, all the E field along this surface must be uniform. Because the distance of on any point on the side to the center, okay, to the center must be the same here because every cross section is a perfect circle. So on the surface to the center must be with the same distance. So to find the field at radius r, we enclose a section of rod with a concentric. Concentric means 同性, okay, with the same center. Gaussian cylinder of radius r, and then the height h. Okay, so this r and h doesn't really important. Yeah, later on you'll see they will cancel out. R will not be cancelled out. H will be cancelled out. Okay, so the net flux through the cylinder from the Gauss law reduced to something like this. Okay, it looks quite simple. Okay, why is it like that? So of course, going back to the original form of the Gauss law, something like this. Okay, something like this. Okay, of course we should try to extract something from this net flux. Okay, so of course there are three surfaces. So the top one, the bottom one. Okay, so this one will be clearly zero. Okay, so the integration of E dot dA for this part must be zero. Okay, the integration of E dot dA for this part should also be zero. Yeah, because the E field is perpendicular to the dA. Okay, it's perpendicular to dA. Okay, so the remaining part is the side. Okay, and as much as we already discussed that, okay, E and dA must be pointing to the same direction. So which means that this E dot dA should be like epsilon naught integration of E times dA. Cosine of 0 degree is 1. Okay, and then E is constant, so it turns out to be epsilon naught E integration of dA. So just like the pure physics example, although the shape is not the same, but it turns out to be something similar. Okay, the formula is similar. Okay, but here is like epsilon naught E times A. Okay, this is A, this one is A. Okay, and then equals Q enclosed. But this A is actually the surface area for the side. Okay, for the side part. Okay, so what is the area? Okay, of course you try to let's say, okay, maybe I erase this part, yeah, because those are zero, not so important. Okay, so here we try to cut it out. Okay, we try to cut it out, something like this, and then you try to expand it. Okay, and then it turns out to be a rectangle. So the height will be h, and then the width will be 2 pi r. The width will be 2 pi r. Yeah, because this is the circumference of a circle. Okay, and you cut it and then you expand it. Okay, so the width will be 2 pi r, and then the height will be h. So the area must be the width times the height, which is 2 pi r h. Okay, so we can see h can be cancelled. Okay, so finally we move this part and this part to the right side. So E turns out to be lambda over 2 pi epsilon naught r. Okay, of course this is not 4 pi epsilon naught r. Okay, maybe okay, if you like, you can actually make it like 4 pi epsilon naught times 2 lambda over r, something like this. Okay, if you like, but actually I just include the equation like this. Okay, just cancel the 2 and 4 partially. Okay, so here it actually means that, okay, so just as what I mentioned, H is cancelled. Okay, so how high the cylinder is, the Gaussian cylinder is not important. Okay, so here what it means is that, of course, this part is a constant. Okay, this part is a very familiar constant. Okay, and then this is the lambda. Okay, which is the charge density. Okay, the charge density. So which means that if the charge density is higher, the generated E field will be linear increase. Okay, so it makes sense. Okay, and then it will be reduced. Okay, so it is inversely proportional to the R, which means that if it is farther away from the rod, okay, the E field is inversely proportional. Inversely proportional. Okay, farther away, the E field will decrease. Okay, so totally makes sense. Okay, so the next case is the planar symmetry. Okay, the planar symmetry. Okay, so here non-conducting. Okay, so previous case is conducting. Okay, and here is it's only a thin, okay, a thin plane. Okay, rather than an infinitely large conductor. Okay, so here we have a portion of a thin infinite non-conducting sheet with uniform surface charge density. Okay, a sheet with thin plastic wrap uniformly charged on one side. Okay, on one side can serve as a simple model. Here applying Gauss law. Okay, so here we just consider, okay, this is very thin. Okay, so even though it should have some thickness, okay, we assume that it is really thin, so all the charge go to one side. So actually here we try to, okay, so here this is that one. Okay, so we also assume that the Gaussian surface is a cylinder. Okay, so half of it is on the left side, half of it is on the right side, and then as much as this one is infinitely large, so that no matter where you place this cylinder is symmetry, so the E field must be pointing to the must be perpendicular to the surface. So which means this part we have a flux to be 0. Okay, integration of E dot dA to be 0. Okay, so we only have this part, and that part will contribute to the net flux. Okay, so starting from the Gauss law, we have epsilon naught EA plus EA. Okay, which means that, okay, similar to what we done before. Okay, only this part. Okay, this part will contribute. So integration of E dot dA. Okay, for this part. Okay, we don't have a circle. It's not a closed surface anymore. So E dot dA, E and dA points to the same direction. Okay, dA points to the right side, points to the same direction. So integration of E times dA, and then E is a constant, so equals E times integration of dA. So it turns out to be E times A for that one. And for the left one is also non-zero because it's a thin non-conducting sheet. So it will generate E field on both sides. So according to symmetry, this one will also have this amount of total flux. So EA plus EA, one is from the left side, one is from the right side. But for the left side, DA also point to the left side. Okay, so which means that EA, DA also point to the same side. So both of them are positive. So we have EA plus EA here. So on the right side, Q enclosed, of course, we assume the surface charge density. Okay, so this is again the surface charge density. Surface charge density. Okay, so sigma times A. So it turns out that A cancel each other. Okay. So on the left side, it is nothing but 2 epsilon naught E, okay? And then we try to move 2 epsilon naught to the right side. E will be sigma over 2 epsilon naught. So this is what we get here. This is what we get here. Okay, this is what we get here. Actually, the same thing. Actually, the same thing. So what it means is that in chapter 22, we derive this one, okay, but with quite a lot of integration. We start from calculate the E field generated by a ring, okay. Of course, it doesn't necessarily use the calculus, okay. But anyway, we need to calculate the E field first, okay, along the z-axis. And then we try to integrate the ring with different radius, okay, so that we can calculate the disk, the E field generated by the disk, and then we try to assume the radius of the disk is infinitely large. So that finally we come up with this expression, okay, so the computation is quite complicated here. Here we try to use the Gauss law. So all the mathematics, we push all the mathematics to the Gauss law itself, okay? So we hide behind the Gauss law. So by using the Gauss law, what we only need is the first step, the second step, and then the first step. Okay, we come up with the same. Expression, okay, same conclusion. So which means that if we have a more powerful mathematical tools, we can it can simplify the computation. But of course, you need to slightly understand, okay, what it means by the Gauss law. Yeah. Okay, maybe we just pause here.